Polynomial Theory, Part 4. The theorems we're going to discuss in this video are Descartes' Rule of Sign, the Intermediate Value Theorem, and Eisenstein's criteria. Descartes' Rule of Sign is stated here. Suppose p of x equal to 0 is a polynomial equation with real coefficients, and with terms written in descending order according to the power on x. Then the number of positive roots of the equation either equal the number of sign variations in the sign of p of x or less that by any even integer. The number of negative roots of the equation either equal to the number of variations in sign of p of negative x or less that by any even integer. Now this statement here is kind of long and it's not the easiest to follow, but I think with an example it'll become a little clearer as to what Descartes' Rule of Sign is trying to tell you. So let's look at an example. Let's use Descartes' Rule of Sign to determine the number of positive and negative real solutions to 2x cubed minus 5x squared minus 6x plus 4 equals 0. If we consider p of x initially and count up the number of sign changes in the coefficients, we have this is a sign change, positive 2 to negative 5. Then we have negative 5 to negative 6, that is not a sign change. And then we have negative 6 to positive 4, and that is a sign change. If we now consider p of negative x, well, that's going to put a negative x wherever I see a x in the original polynomial, and then I'll have to raise those to the appropriate powers and consider the sign after this is completed. A nice little hint here is that only the odd powers of x change sign, so any even power of x or constant will not experience a sign change with the substitution. So you only need to change the signs on the odd powers of x. So we'll go ahead and do that, and that's what's done here, and we'll count up the number of sign changes in the coefficients. And when we do that, we have from negative 2 to negative 5, that is not a sign change. From negative 5 to positive 6, that is a sign change. And then from positive 6 to positive 4, and that is not a sign change. So counting up the sign changes for p of x gives 2 sign changes. So there are 2 or 0 positive real solutions to that polynomial. And this is what they mean by taking the number of sign changes less than even integer. We're going to subtract 2 from the total number of sign changes, and then we're going to keep subtracting 2 until we get to either 0 or 1 for the number of possible solutions to the polynomial. Counting up the sign changes for p of negative x gives 1 sign change. So there is 1 negative real solution to this polynomial. So Descartes' Rule of Sign guarantees the existence of 1 negative real solution to the polynomial. Since the degree is 3, there must be exactly 3 solutions. So this table summarizes which sets the solutions could belong to. We have 2 positive, 1 negative, and the sum of that would be 3, which means that there would be no imaginary solutions or no complex solutions. We could also have 0 positive solutions, but we are still guaranteed 1 negative real solution. And if that's the case, then the other 2 solutions must be imaginary or members of the complex number system. To the right is a graph of the polynomial. We can see that we have 1 negative real solution, which is circled here in blue. We can also see there are 2 positive real solutions, which are also now circled in blue. The intermediate value theorem is stated here, and it states that a function, f of x, that is continuous on a closed interval, ab, takes on every value between f of a and f of b. We will use the intermediate value theorem to help us locate roots to polynomials by creating bounds tighter than the bounds theorems. As an example, let's determine if there is a solution to the polynomial 2x cubed minus 5x squared plus 6x plus 4. Now, bounds on zeros theorems suggests that all roots are in the disk of radius 4, but it doesn't say anything else. Descartes' Rule of Sign allows us to conclude there are 2 or 0 positive real solutions and 1 negative real solution. Since we know this information, let's determine if there is a root to p of x between -2 and 0, and here's how. The first step is we will compute the value of the polynomial at x equal -2. And when you plug -2 into the polynomial, you get -44. Our second step is to compute p of 0, and that means we're going to put the right endpoint of our chosen interval into the polynomial. And when we do p of 0, we simply get +4. Our third step is to use the intermediate value theorem. And here, what we're going to look at is we're going to look at the output of our previous two steps and see if there's a sign change. And since there is a sign change in the endpoints of the interval, and polynomials are continuous functions, we may conclude there is one root to this polynomial in the interval -2, 0. Now, Descartes' Rule of Sign guarantees us the existence of a negative real solution, and now the intermediate value theorem has given us a place to start looking for that between -2 and 0. There are situations when the intermediate value theorem can fail to provide answers, and these are demonstrated on the next slides. If we look to the graph to the right, this is an example where the endpoints of any interval chosen would not change signs. So here we can see that our graph here virtually bounces right off the x-axis. But if I try to choose endpoints for an interval, the function evaluation just doesn't change sign. So notice there is a solution at x equals 0. But the intermediate value theorem cannot be used because the conditions are not satisfied. This particular example violates the condition that there would have to be a sign change in the output values at the endpoints of the interval for us to start drawing conclusions and saying there are going to be solutions somewhere in between. This next example violates the continuity requirement of the intermediate value theorem. So there is a solution at x equals 0, but the intermediate value theorem cannot be used here because, again, the conditions are not satisfied. So in order to use the intermediate value theorem when it comes to polynomials, you have to have a continuous function, and you have to have a sign change in the output values at the endpoints of the interval that you're using. Eisenstein's criteria is used to determine if there are rational solutions. Now, this is usually not discussed in a college algebra class, but I discuss it here because it is a theorem that helps us out with the rational zero theorem, and it's also not very difficult to apply or understand. So the rational zero theorem is a theorem that determines all possible rational solutions when the coefficients are integers. There are some drawbacks to the rational zero theorem, though. The list may be long. For example, if your leading coefficient is 1 and your constant term is 72, then you have 24 possible numbers to check to see if any of them make the polynomial equal to 0. The second drawback is that the polynomial may not even have rational solutions. The rational zero theorem does not speak to this at all. So, for example, x squared plus 1 has integer coefficients, but it doesn't have rational solutions. Both of its solutions are complex. So Eisenstein's criteria can be used to determine if rational zeros even exist to specific polynomials. There are more advanced theories in algebra, but this theorem uses only tools practiced at an introductory level, and we'll see that there are very few conditions to satisfy that are not beyond the scope of most introductory classes. So here's the statement of Eisenstein's criteria. Let f of x be a non-constant integer coefficient polynomial. So we still have integer coefficient polynomials, just like the rational zero theorem. If there is a prime number, p, such that p divides all the coefficients except the leading coefficient, and p squared does not divide the constant term, then f of x has no rational solutions. Now let's see this theorem in action. Determine if the polynomial x to the 10th plus 6x to the 7th minus 15x to the 4th plus 3x squared minus 9x plus 12 has rational solutions. Our answer is that we're going to apply Eisenstein's criteria, and we just go right through these four questions. Does this polynomial have all coefficients that are integers? And the answer is yes. These are all integer coefficients, so we satisfy the first condition for Eisenstein's criteria. The second step is to determine if there is a prime number that will divide all of the coefficients evenly except the leading coefficient. So our coefficients are 6, negative 15, 3, negative 9, and 12. And all I need is a prime number that will divide all of those evenly, and the answer is yes, there is one, and 3 happens to be our choice. The third step is to ask, does 3 divide the leading coefficient evenly? In this case, the leading coefficient is 1, and 3 does not divide 1 evenly, so the answer to that is no. Our last question is, does 3 squared divide 12 evenly? And the answer to this is no. 3 squared is 9, and 9 does not divide 12 evenly. Because we answered all the questions Eisenstein's criteria asks correctly, we may conclude there are no rational solutions to this polynomial. And these are the four questions that need to be answered. And those are the answers that say, hey, we now know that there are no rational solutions. There's no need to apply the rational zero theorem. The importance of satisfying conditions. Here we're going to present two examples of polynomials. Both do not satisfy all the conditions of Eisenstein's criteria, but one will have at least one rational zero and the other will not. And this kind of demonstrates that you really do need to answer all four of those questions in the answers that I provided here for our example before we are guaranteed by this theorem that we have no rational solutions. And again, theorems are about guarantees. If we satisfy all the conditions of the theorem, then we are guaranteed the conclusions. Otherwise, we cannot use the theorem to get our conclusions correctly. Let's take a look at this example. Here we have a polynomial of x cubed plus 2x squared plus 8x plus 16. Now, the conditions are not satisfied for Eisenstein's criteria. We have integer coefficients, so that one's okay. We have found a prime number that will divide all of the coefficients except the leading one, and those coefficients are 2, 8, and 16. 2 is a prime number that will divide all of those, so that condition is satisfied. The leading coefficient is 1 in this case, and 2 does not divide 1, so that condition is satisfied. But 2 squared is 4, and 4 does divide the constant term 16. So that condition is violated. So what can we say? Well, we can't say anything. Using this theorem does not apply because we did not satisfy all the conditions. This polynomial, though, does have a rational solution. It happens to be at x equal negative 2. So in this case, we did not satisfy the conditions of no rational solutions, and this polynomial has one. So we didn't satisfy all the conditions, and we found a polynomial that does have a rational solution. So what does that lead us to conclude? Well, if we take a look at this example, x cubed plus 2x squared plus 4x plus 16, this one also does not satisfy all the criteria from Eisenstein's criteria. We have integer coefficients. Our prime number p equal to 2 still divides all of the coefficients except the leading one. P squared equal to 4, and 4 does divide 16. So we violate the exact same condition that we did in the previous example. But this time, this polynomial does not have any rational solutions. All of its solutions are either irrational or complex. If you do not satisfy the conditions, you cannot use the theorem. Okay, this is a very, very important statement because a lot of students like to use the converse of a statement. You know, if you don't satisfy the conditions, then the converse of the conclusion must be true. That is not the case at all. And that's the importance of satisfying the conditions, and that's why these two examples are demonstrated. You may or may not have the conclusion satisfied if you don't satisfy the conditions. And that can't work in logic or mathematics. So if you do not satisfy the conditions, you cannot use the theorem. It does not mean the converse is automatically true. And here we have two examples, the same condition violated in Eisenstein's criteria, but one polynomial did have rational solutions and one polynomial did not. So you have to satisfy all the conditions before you can draw the conclusions, and that's true for any theorem. Thank you for your time and attention.